Hi everyone, I'm Hank Stevens, and welcome to my talk entitled Mesoamerican Tree Species Composition Suggests Alternative Stable States. This work is actually the brainchild of Dr. Nancy Ross, an ethnoecologist at Drake University. This work that I'll be presenting today was also the result of work by several others, including Leopoldo Romero, Don Heriberto Cocom, and Mary Murillo. We live on a used planet. Humans have been ecosystem engineers and changing this planet for millennia. While we're continuing to increase our impacts on the planet, unfortunately, there are in fact some areas that are actually recovering from past peak use, and nearly all of these areas still show what we call human landscape legacies. One of these landscape legacies that you might be familiar with is that of the ancient Maya. The Maya created a very dense human civilization in Mesoamerica that re-engineered through a variety of mechanisms much of the Mesoamerican landscape. The legacy that Nancy and I are studying is referred to as forest gardens, labeled here as settlements and orchard gardens. These occurred in the vicinity of residential areas surrounding urban centers and were managed forests that provided much of what the Maya needed to thrive, and we wind up comparing these to older forests in the surrounding forest matrix. Here we have an abbreviated display of the types of products these forest gardens provided. Along the horizontal axis, we have some of the woody species that the Maya used, and along the vertical axis, we have a list of some of their uses, including medicines, ornament, food, and construction. The Maya nurtured these species to ensure their continued use, and we refer to these species and species like them as garden species. Species that weren't prized by the Maya we refer to as non-garden species. Unfortunately, changes in climate increase, drought, and other factors led to the collapse of the Maya civilization over 1,000 years ago. So, what happened to these forest gardens? And that is our question. So here's a cartoon of possibilities. As a comparison, let's assume that the surrounding forest matrix outside residential areas, due to its pervasive size and intrinsic dynamics, continued to replace itself, and we show that here on the left side of the screen, where we have low settlement density or no settlement densities in the forest matrix, and that continues on. However, so what happened to those forest gardens? In the absence of any other mechanisms, we'd have to think that they simply revert to a relatively undisturbed condition, becoming more and more similar to the forest matrix, indicated here by these diagonal arrows of the forest garden reverting to forest matrix. But what if there were other mechanisms at play? What if something else caused them to remain as they were, and at least retain some of the characteristics that they once were? So now we'll describe the process that we think may actually help the characteristics of these garden forests persist today. So imagine that as the Maya established a settlement in a forest, they began to nurture some of those species that they found useful. And we'll illustrate this with a tree with blue fruits, and we show that the forest garden has more of them. At first, this leads to a proportional increase in the number of frugivores that also use this species. And these frugivores, of course, are critical for the continued dispersal and the maintenance of this species. However, this extra high abundance of this fruiting species actually draws in a proportionally higher abundance of frugivores. The abundance of fruit crosses a threshold that draws in proportionally more dispersers. At that point, this blue species becomes what's known as a hub species that anchors the mutualist network and on which many other species depend. As dispersers are drawn in, they bring with them seeds of other species, leading to a positive feedback loop between fruiting trees and frugivore dispersers, resulting in what Lazaro and colleagues referred to as a bird-made orchard or simply a bird orchard. This frugivore behavior creates spatial contagion or clustering of fruiting species that the dispersers prefer, and we should be able to see this spatial contagion among pairs of garden tree species. This positive feedback loop has then established the mechanism which maintains features of these forest gardens to this present day. This creates what dynamicists call alternative stable states. Now, demonstrating alternative stable states is notoriously difficult, and ecologists have identified key criteria to help guide the way. The first of these is the physical environment, and the second of these is the potential species pool. So the physical environment and the potential species pool must be the same in the two community types, and we see that represented in the figure on the right, where we have the states on the horizontal axis, so perhaps the forest matrix on one side in one basin of attraction, and the garden forest in another basin of attraction. Then lastly, given a single set of environmental conditions for both of these community types and a single set of state variables, such as a single species pool, the last criterion is that we have to have resilience of more than one equilibrium. That is, the community must return to that point if it's disturbed. So in our study system, we hypothesized that the Maya altered tree species abundances in a way that drew in more frugivores, which created an ongoing feedback loop that helps maintain many of those garden species at high abundance today. And we argue that our study system meets those first two criteria. And today I'll show you data that provides descriptive evidence for the third. So Nancy, with the help of Leopoldo Romero and Don Heriberto Cocom, surveyed all palms and trees in 63 20 by 20 meter plots in western Belize and eastern Guatemala. Of these, 31 were in ancient residential areas, what we refer to as high settlement density areas. These are the residential areas, or the former residential areas. The other two plots were in areas where Nancy and her colleagues could find no evidence at all of any former settlement, and we refer to those as forest matrix sites. In each plot, they ID'd, mapped the locations of, and measured the diameters of all trees at least 1 inch in diameter. They sampled the soils for a variety of characteristics, and importantly, they found only very minimal differences in the soils of the two types of sample plots. And this absence of substantive difference in the physical environment is an important assumption of alternative stable states. Another important feature of this environment is that there's a relatively high disturbance frequency. Long-term geological and ecological studies show that the area gets hit with major hurricanes, categories 3 to 5, about 10 times per century. So this suggests that species composition of these garden forests is at least moderately dynamic and has had the potential to revert to matrix forest. One assumption of our hypothesis is that Maya garden species should produce more fruit than non-garden species. And to evaluate this, we scoured the literature for information on the fruiting phenologies of all the species in these plots, garden and non-garden alike. For every species we could find, we recorded the months in which these species were shown to have produced fruit. We then combined this with monthly fruiting data with total basal area of each species in each plot to calculate an index of fruiting potential for each Maya garden species and non-garden species, and then sum these to get a total aggregate fruiting potential for each type of species in each plot for each month. We then use these data to compare the fruiting potential of garden versus non-garden species. So our hypothesis relies on and generates a number of assumptions and predictions, and 6 of which I've listed here and for which I'll show you data. We conducted Bayesian analyses in R using a variety of packages, including mostly R2JAGS and RSTAN-ARM. First, we found that garden species had higher basal area relative to non-garden species in those garden forests. The figure on the right shows on the vertical axis the log ratio of the basal area of garden to non-garden species for each forest type on the x-axis, garden forest and matrix forest. Values greater than 0 indicate dominance by garden species. Each point in the figure represents data from a single 20 by 20 meter plot. We found that the dominance by garden species was greater in the garden forests, thereby showing that these forests have not disappeared in spite of the high disturbance frequency and dispersal from surrounding forests. Second, we found that garden species comprise a greater fraction of animal dispersed species. The figure on the right shows the log ratio of animal versus other dispersal mechanisms exhibited by each species type. Non-garden species on the left and yes, garden species on the right. Analysis showed with 95% confidence that garden species on the right had a higher fraction of animal dispersed species. Third, we found that when garden species occur in garden forests, they probably act as hub mutualists, anchoring mutualism networks in garden forests. The network figures on the right are based on spatial contagion between pairs of tree species, indicated by the abbreviations there, and shows links between species with significant spatial contagion. And the spatial contagion typically arises due to shared dispersal vectors, where animal dispersers deposit seeds in a non-random way, creating contagious patterns of shared fruit resources. The top network is for garden forests, and the bottom network is for the matrix forests. The font size of the species abbreviation indicates the number of connections for that species. These show the garden species are much more likely to show spatial contagion when they occur in those garden forests. Fourth, total aggregate community fruiting potential, seen here on the y-axis, was much higher for garden than for non-garden species. In the figure on the right, months are arrayed along the x-axis while fruiting potential is on the y-axis. The smooth curves just include 95% credible intervals for each month. So recall that fruiting potential is the aggregate basal area of all species shown to fruit during each month. Fruiting potential goes up and down, but is in total much higher for garden than for non-garden species. So this shows that, indeed, garden species provide a greater resource for animal dispersers than do non-garden species. In addition to the totals, the minimum fruiting potential was much higher for garden than for non-garden species. If garden species provide a reliable resource for frugivores that disperse the fruits, then having a higher minimum fruit production helps maintain some minimum base level for frugivores. Sixth and last, we also find fruiting potential for garden species was less variable than for non-garden species, again providing a more reliable resource base. The figure on the right shows the coefficient of variation from month to month fruiting potential for non-garden and garden species, where each point in the figure represents data from a single 20 by 20 meter plot. We see that the aggregate fruiting potential of garden species on the left tends to be less variable, on the right, the fruiting potential of the garden species is on the right. That tends to be less variable and thus potentially more reliable for the frugivore dispersers. So, last, I've shared some of our preliminary evidence for alternative stable states in Mesoamerican forests, and I hope that I've piqued your interest in these ideas. First, that we can characterize myriad human landscape legacies, hundreds of different details about human landscape legacies in the relatively simple terms of classical dynamics. And if you want to learn more about that, I suggest you take a look at Ross and Stevens' 2019 in American Journal of Botany. But second, that mutualist-driven alternative stable states might underlie the long-term persistence of these Maya garden forests. Our next steps include field observations that will quantify actual fruiting phenologies rather than information we culled from the literature. Also, quantify actual frugivore communities, and last, frugivore plant interactions. So thanks very much for your attention. I'd be happy to try to answer any questions you might have. Send your emails for Nancy Ross and myself to one of our emails, and we look forward to hearing from you.